Hello, so we are going to now be looking at Chapter 11, which deals with the concept of integration. Please have the notes printed out so that you can follow along with the examples. So the first thing is, what is an antiderivative? Well, if you're given a function, it's going to be the antiderivative of another function if you can take the derivative of that capital letter function f and end up with the lowercase script f function. So, okay, what the heck does that mean? Well, let's look at an example. Okay, so what we're trying to do in this example is show that this capital letter f function above is in fact an antiderivative of this lowercase function f as shown here. So what we have to do is just look at this given function, the capital letter f function, and then take the derivative of it. So what is the derivative of capital F of x? Well, basic rules of differentiation, still, obviously we should still know how to do that. Bring down the 4, we get x cubed. Take 1 away, getting x cubed. Bring the 3 in front here, take 1 away. We get minus 3x squared. And then we get, of course, plus 10x. So since the derivative of capital letter f is equal to lowercase f of x, then this function, capital F, is called an antiderivative of this function, lowercase f. This theorem is telling us that there are really infinitely many antiderivatives that exist based on a given function. Look, you're not going to have to know these theorems on a test, of course. You're ultimately just going to have to be able to come up with the antiderivative or integral. As we progress through this chapter, you'll see that. But anyway, just to go over this example, if you took the derivative of this function g, you're going to get this result, right? So it just so happens that if you looked at the function g in this form, so there's your capital letter f of x equals what's g? Well, it's x cubed, that's given. If you added a c to this, which is any constant, and took the derivative of this function, you're still going to get this. So this is just representative of a whole family of antiderivatives that exist based on, the given function g and what we get as a result of deriving that. So after you've studied your basic rules of integration, which are in the notes, hopefully you, again, have those available, we are now going to apply those to several examples. So the first one is in front of you, letter A. So what we're going to do first is rewrite this so that the variable x is in the numerator position. Forgot the dx here. So actually, before I go any further, this is the integral symbol. It means we're going to be integrating something. This is called the integrand, what we're integrating. This 1 over 3x to the 5th is what we're actually integrating. And this just means with respect to x. Okay, it's the differential of the variable x. But again, all this means is we're going to be taking the integral of this function with respect to x. So after you've studied your basic rules of integration, which are in the notes, hopefully you, again, have those available, we are now going to apply those to several examples. So the first one is in front of you, letter A. So what we're going to do first is rewrite this so that the variable x is in the numerator position. Forgot the dx here. So actually, before I go any further, this is the integral symbol. It means we're going to be integrating something. This is called the integrand, what we're integrating. This 1 over 3x to the 5th is what we're actually integrating. And this just means with respect to x. Okay, it's the differential of the variable x. But again, all this means is we're going to be taking the integral of this function with respect to x. So the first thing is to move that base x from the denominator position into the numerator position, making it x to the negative fifth. The next thing we're going to do is if we have any numerical coefficient here, any number in front of x, and it's just a single term here, we're allowed to move that number in front. In front of what? In front of the integral symbol. So now we have this. And the next thing we're going to do is apply the second basic integration rule. So look at your notes there, the second basic integration rule. And what that tells us is we are allowed to do what? If you have x to the negative fifth, you're allowed to do what with that? What you're allowed to do is this. You're going to add 1 to the exponent, and then you're going to divide the whole thing by whatever this result is. So I'll go ahead and show you what really is going on. And then you're going to always add c to it like we talked about in a previous example. So in this case, your final result would be 1/3 times x to the negative 4 over negative 4 plus c. At least this is what you'd get when you integrate x to the negative 5. Again, all you're doing is you're going to add 1 to this negative 5 first. Change the exponent first. Add 1 to this, make it negative 4, and then divide by that new exponent, which is negative 4. Finally, just simplify this if you can. So I don't care if you leave it in terms of a negative exponent, that's fine, but this would be your result. These are all called indefinite integrals because there are no upper and lower bounds. So if you don't see any numerical values here or here on the integral, then handle it accordingly. And of course, you'll know what I'm talking about once we get to that point in the book. So if you don't have any numerical values here or here, you will always add c to your final answer.